Hey, Debbie, can you see and hear us okay?
We can. Can you see us?
Yep. Thank you very much.
You're welcome.
So the first thing today is we got test 1. And that's going to happen on Thursday. That's 21st. It's going to cover chapters 1 through 6. Now, you folks that are with Rob in Johnson City, you'll be there with Rob. You folks that are here with me, you'll be here with me. You folks that are streaming, I sent an email last Thursday. And again, if you told me you're going to Johnson City, you're going to Sam Wilson 202. If you told me you're coming to Kingsport, we're in room 232. If you're using a proctor, I'll be emailing the test and the answer sheet to your proctor sometime tomorrow, right, Wednesday. So here's what's going to happen with your test. Your test has got 40 questions, it's multiple choice. It's A, B, C, or D. I don't do all the above or none of the above. I told you that last Thursday, right? So the answer's actually sitting there looking at you. You need to bring some version of an ID in case somebody wants to see it, a calculator, and your 6, I'm just going to do this. There's 6 pages of those tables and formulas you printed out. Make sure you bring those. I mean, you can have those for the test. You're definitely going to need that table A that we keep using in chapter 3. And then the other thing I have is tonight, before I leave, and after we get through class, I'm going to post my thoughts for test 1. It's in D2L under content, the syllabus. I would have already posted them, but I didn't know how far we were going to get in chapter 6, so I'll show you where they're at just in a second here and show you what I mean by my thoughts, all right? So there we are. I'm in your site. It's under course content, and I go to the syllabus, and there's right here, there's thoughts for test 1. So what do my thoughts look like? I try to remind you the things we've done all the way through. Like I grouped 1 through 3 together, 4 through 5, and then 6 is kind of its own little thing there, right? It says, be able to identify the who and the what. Go back and look. That was like the first thing we ever talked about. Be able to identify the data, categorical, quantitative. How do you describe categorical, bar graph or bar chart? That's your graphs. So that's what I've done. I don't have any particular problems in my mind here, but these are the things you need to be able to do. And when you're looking, here's what I do. When I'm making the test, I'm looking at this going, oh, I need a problem that does that. I need a problem that does that. And so what I do is I take problems that are very similar to the ones you've done for me and turn them in for homework, and I turn them in the multiple choice questions. That's just the way it is, right? And then 4 and 5, be able to interpret the correlation, know the facts that I wrote down, regression, interpret the slope, y-intercept. I mean, I've done 3 or 4 or 5 problems like that. That's what you're going to have here, right? So the reason I scrolled down to 4 and 5 is when I want you to have a scatter plot, I'll put it there. If I want you to have the regression line, you know the one I always show you with the scatter plot, it's got the regression line and all that? That's the one I'm going to use. Then I'm going to start asking you questions about it. Can you interpret this? Can you tell me about the slope and all that? Can you use the line for prediction? In other words, can you plug in a value for x? Can you calculate a residual if I give you a point that's actually on the scatter plot? That's what's going to happen here. And then chapter 6, there's only one little thing there, because I wanted to make sure we could get to it. So I'll make this available when we're done here tonight, just to make sure that I get far enough, okay? So where was it? That was content, syllabus, my thoughts for test. And if you get home tonight, it's 10 o'clock and you didn't see that shit, would somebody please email me and say, dude, you forgot to publish it? Okay? No, that's because it's not published yet.
Oh, okay.
No, I was just showing you where it is. She's telling me she can't see it on hers. Yeah, you can't see it. Nobody can see it yet, because I didn't actually make it available to you because I didn't know where I would end up in case I needed to take something away. All right? And I'll know after class tonight where we're at, and so then I can post it to you. Okay? Now, I want to go back, and I got a couple things to say about chapter 5 right at the end. Remember I asked you to read that last Thursday? And I'm going to make this kind of short and to the point. I'm thinking about cautions here, and the cautions are about two things we've talked about here: correlation and regression. The least squares regression line, right? That's always the line me and you deal with. And I'm going to start numbering here. And the first one is, both of these describe only linear relationships. And that's all. They don't tell you about any other form other than linear. So I'm going to underline this just to remember, what does correlation tell me? It tells me the strength and the direction, right? The sign tells me the direction, and the strength is you get stronger as you get closer to -1 or 1. The regression line, I'm going to give you, obviously only describes a linear relationship because we're trying to fit the line to the data, right? It won't tell me about anything else other than those. That's actually a caution. And two, something we talked about last Thursday is, both of these are not resistant. Remember, I keep using that word resistant when something's influenced by outliers in this case. Okay? So what we do is this. We always make sure we plot your data. That's what we do in this class all the time. We always want to make a graph of whatever we're looking at. And let me ask you this. What's my only plot for my data here? It is a scatter plot, right? Because we're looking at two quantitative variables. And what we're going to do is we're going to plot our data. We're going to look for influential observations. You know, the ones that would markedly change the calculation of correlation or the calculation of the least squares regression line. I showed you those on that little app last week where I can make everything move depending on where the outlier was. So we're looking for ones that are influential. Now, these two things here, we already knew this. I'm just kind of summarizing that. The third one is something called extrapolation. And what this means is trying to predict outside the range of X values in the data. This is a no-no. We never do this. We don't do this. In other words, I kept pointing you to this every time I looked at a scatter plot with the regression line and everything on there. I said, okay, so what does it look like, the range of my X values are? In other words, like, what's the range of the values of my explanatory variable? If they're here, we don't go out here and we don't go out here, right? We always want to predict inside the range of X values that we have in the data. We don't want to go outside of there. The reason for that is that's where we fit the line to the data. Outside of that range, I don't know if what I'm looking at is still linear, is still approximated or summarized by the line I have on there. All I know is what I'm looking at, and if that's my range, I will not go outside of it. How many times I got to say that? So on Thursday, when I give you a scatter plot, and I put the regression line, and there's the equation, and I say, for what range of values would you like to use it to make predictions? I can't remember what number that is on the test. Whatever you see there, right? So I'm moving like this. Here's my X, and here's my range of values. That's what you tell me. Because why? We never extrapolate. We never go outside that range. Okay? 4. This is something I had spoken with you about beginning of chapter 4. And there's a definition here of this on page 147 in your text. It's in a little box. I'm going to read it to you. It says, a lurking variable is a variable that is not among the explanatory or response variables. In other words, it's not what the variables we're actually looking at, but it's still a variable in a study and yet may influence the interpretation of relationships among those variables. Remember the one I gave you this and I said, please remember lurking variables was, we were looking at the height of a woman having some kind of, saying something about her risk of heart attack, right? And we ignored her exercise habits, her diet, how often she went to the doctor. Those three things on this hand right here are all lurking variables, right? There's something that could have been measured, but we ignored them. I got to look at example 5.7. This is the one that always makes this stick in my head. The Kalamazoo Michigan Symphony once advertised a Mozart for Minors program with this statement. Now, I got to warn you about the author of our textbook. He ain't making shit up. This is true, right? Question. Which student scored 51 points higher in verbal skills and 39 points higher in math? Answer. Students who had experience in music. Who knew that if I gave my child experience in music, they would be good with verbal and would be good at math? Well, what's the story here is, obviously there's some lurking variables here that we are ignoring. We could as well said students who played soccer. Why? Children with, this is my left hand here where I start marking lurking variables down, with prosperous and well-educated parents are more likely than poor children to have experience with music and also to play soccer. They are also likely to attend good schools, get good health care, and be encouraged to study hard. These advantages lead to high test scores. Family background is a lurking variable that explains why test scores are related to experience with music. All those things I just talked about there, those are lurking variables, and they're having an influence on what we're seeing with having experience with music and being good at math and verbal skills. Okay, so this is all well and good. Okay? We're always, and I'm going to underline this for you, I'm always concerned when I'm picking out two variables to look at the relationship. I always think about this idea of a lurking variable, right? Are there anything lurking in the background that may have an influence on this relationship, either way that we're not paying any attention to? And then the fifth one, I don't have an overly lot to say about this one, because me and you are going to spend a whole chapter on this one. And what I have is this. Association. Does not imply, and it's the term here that they use, causation. Okay? So when I think of this term causation, here's what I think. I'm going to translate it a little bit into, I think about cause and effects. And what I mean by this is, if I start making changes in your explanatory variable, will that actually cause a change or have an effect on the value of your response? One actually causes or has an effect on the other. You want my first example of this? I can start changing your blood alcohol level by changing the number of beers you drink. That's about as cause and effect as we can get. Now, I got to look at the example here because I always like this one. And every year when I get older, I like these things more and more. I want to look at example 5.8. Does having more cars make you live longer? A serious study once found that people with 2 cars live longer than people who own only 1 car. Owning 3 cars is even better, and so on. There's a substantial positive correlation between the number of cars X and the length of life Y. In other words, you've got 2 quantitative variables. When they say there is a substantial positive correlation, it means it's close to 1. In other words, there's a very strong positive linear relationship between the number of cars you own and how long you live. And then, so the question is, do we have evidence here of cause and effect? Can I change how long I live by owning more cars? It's a dumb question, right? I always hope the answer was yes, because I just go out and start buying my ass more cars, but the answer is no. There's not evidence of cause and effect here. It says, The basic meaning of causation is that changing y will bring about a change in, changing x will bring about a change in y. Could we lengthen our lives by buying more cars? The study used the number of cars as a quick indicator of affluence. Well-off people tend to have more cars. Here's my left hand again. They also tend to live longer, probably because they are better educated, take better care of themselves, get better medical care. What are these three things in this hand again? These are lurking variables that everybody decided to ignore and let's just count the number of cars and let's have a relationship with how long you live. These other three things may have a better explanation of why people live longer that have more cars than just having more cars. It says these are lurking variables. We're done. Here's my thought. I don't know how I'm going to get you to remember this, right? It does not imply. I don't care if the correlation is a +1 or -1 where it's perfect, you still don't have evidence of cause and effect. So, what do? The best way to find evidence, and I'm going to put the word good in front of this, of causation. This idea that changing the value of one of the variables, your explanatory variable, will cause a change in your response variable, your y. The best way to find good evidence of causation is performing a well-designed experiment. And what chapter is that? Like I said, me and you get a whole chapter of that. That's actually chapter 9. We're going to spend the whole chapter with this thought of causation and how do we actually set up a well-designed experiment so that we can find good evidence that if I make changes in my explanatory variable, that it actually causes a change in my response variable. Okay? Now, I had asked you to read this, so I'm going to assume you did. I'm going to assume you read the thing about smoking causing lung cancer and all this. I'm going to kind of leave this where it's at now and remind you one more time, all these things I have listed, and I listed, what was it? I listed 5 of them. These are cautions dealing with correlation and your regression line, your least squares regression line. We will come back and we're going to talk a whole chapter about number 5. We always have it in the back of the head about lurking variables, and please don't extrapolate. Don't go outside that range of x values that's in the table. All right? I'm going to leave this chapter there. All right? Now, chapter 6. We're still dealing with 2 variables at a time. Except in chapter 6, there's something called TwoWay Tape. Now, where we're changing here is what we're looking at, and what we're going to focus on at this moment is 2 categorical variables. Just to remind you, in chapters 4 and 5, they were both quantitative. Here, they're both categorical. So, what's a categorical variable? Let's review for Thursday. What's a categorical variable? It's one that puts you in a category or group, like your gender, your race, your occupation, your major, your eye color, your hair color, all those kinds of things. Okay? Now, here's the thing about categorical data. To analyze categorical data, I don't care if you're looking at 1 categorical variable or 2, we always use counts or percents. In other words, what am I talking about? We're talking about the count of individuals that fell into a particular group or category, or the percent that fell in a particular group or category. And I'm going to be completely honest with you. I like percents. Right? So I always want to think about calculating some percentage in this group, some percentage in that category, that kind of thing. Now, when you are looking at two categorical variables, there's a very nice way the data comes to us. And I want to look at this example, 6.1. It says that in 2015, the National Center for Education Statistics projected the number of academic degrees to be awarded in 2017 and 2018 for men and women. Table 6.1, and I'm going to mark that down for you, because that's where I want you to look, and it's on page 164. It's at the top of 164, right? There's a table there. It says this, shows these projections, their projections. This is a two-way table. Why is it a two-way table? It's a two-way table because you're classifying everybody in your data set by both the categorical variables. Now, when I look at this two-way table, there's a couple things I want to be clear about. The row variable here, in other words, what I want to know is how are the rows broken up? That is by a person's sex or their gender. There's actually two rows in the table. It's either women or men. And then the column variable, how are the columns broken up? Well, the columns are broken up by the degrees conferred. In other words, I'm just going to say degree. What kind of degree did the person earn? Now, you'll notice in parentheses there it says thousands. So when I look at this table and I see a number like 673, the actual number is not 673, it's 673,000, right? They marked off those last three zeros just to make the numbers easier to deal with, okay? Anytime you're looking at a two-way table, one of the categorical variables will be the row variable. The other categorical variable will be the column. Does it matter which one's which? And the answer is no. One of them needs to be the rows. One of them needs to be the columns. Okay? Now, here's the other thing I see. I always like to talk about a two-way table as follows. I like to give the number of rows by the number of columns. And I don't care about the total, because this table here, it's total the columns for us, it's total the rows. In other words, there's an extra row and an extra column there that's irrelevant to me. They just made my life a little bit easier here. And so in this case, what I see is how many actual rows there are. What I'm asking you is how many categories are there for sex or gender? That's a 2 by, how many columns are there? That's not actually the total. There are 4 columns. So that is a 2 by 4 table. 2 rows, 4 columns, and all I'm really telling you is there's 2 categories for the row variable, there's 4 categories for the column variable, and everybody who we're looking at here, and we're looking at the degrees awarded in 2017 and 2018 for men and women, have been classified by their sex or their gender and by the degree that they were going to earn. Okay? Now, I got to take this one step further, just with some more language. When I say a 2 by 4 table, that means there are 8 cells in that table. And the way I would number the 8 cells in the table is I would do this, right? So, my table looks like this. That's cell 1, 2, 3, 4. Remember, there was 4 columns for the first row. And then I would come down here and number 5, 6, 7, and 8. Remember, I don't really care about the total. That's not really part of my two-way table. That's just somebody making my life a little easier here by summarizing and adding shit up for me. All right? So, I could be sitting here and I could ask you, okay, does everybody see cell 3? What's he talking about by cell 3? Well, if he numbers it like that, cell 3 is going to be what? That's going to be women that did what? Earned a master's degree. Everybody understand how I'm reading this, right? So if I think about numbering like that, obviously I'm in the first row, I'm in the women's row, I'm in the third column. The third column there is the master's degree was conferred. All right? And so then what I want to know, can everybody everywhere pick the number out in cell 3, the ones that we're looking at have been classified as women and have a master's degree? How many is there? 481. Obviously, that's actually 481,000. The number in the table is 481, right? That is cell 3. Is there anything special about cell 3? Let's do another one. I just want to make sure we can read the table. If I tell you I'm looking at cell 5, what row am I in? I'm in the row where we're looking at men, and I'm in the first column, and the first column here is associate degree. When I look at my table and see, okay, how many have been classified as men and have an associate's degree or would have earned an associate's degree, there is 40. Okay? We're picking them out. Now, you see these numbers here that's in the table. Those are not percentages, those are counts, right? It's how many. Now, what do I want to do with this two-way table? Well, I want to do two different things with it. Because look, anytime somebody's going to give me data on individuals and you're going to classify them by two, can I use the word classify? I mean, I could use the word categorize, I could use group, but I always think about classifying them by two categorical variables. One of them needs to be the rows, one of them needs to be the columns. This stuff about me calling this cell 3, cell 5, the book's not going to talk about that. I just wanted to give you some language so that me and you can be speaking about the same thing. I like the idea of the number of rows by the number of columns to tell me that's a 2x4 table. So then I know you're talking about 2 rows and 4 columns, right? And I know how to number them to tell you that I'm getting 8 cells here. Look, suppose I had a 3x3 table. I had 3 rows and I had 3 columns. How many cells would I have? I'm asking you, do you know how I got the 8 cells? I multiplied, right? 2 rows by the 4 columns give me 8. Okay? Now, with that said, now we're ready to start calculating percentage. Notice that table is giving me counts. That's the reason I wrote that back there. So look, there are 2 types of distributions when you're looking at a two-way table. The first type is something called marginal distribution. And I got this really dumb thought. The reason they're called marginal distributions is because they are using the numbers in the margin of the table. In other words, they're using row totals and column totals. Those are the margins of your table. Now, anytime you're given a two-way table, marginal distribution, always 2. 1 for each variable. In other words, there is a marginal distribution for the row variable. There's a marginal distribution for the column variable. What do? We ignore the other one. We look at each variable by itself. We look at each variable, what we're going to do separately. So here's what I want to do. I want to look at this two-way table, this table 6.1, and I want to calculate both of these for you to see, okay, if we're going to do anything here, we're going to calculate a bunch of percentages. So I would like to look at the marginal distribution of a person's gender or their sex. Right? So I want the marginal distribution of your row variable here. So what's my possible categories, my groups? It's either women. I kind of like to do it like this. And then anytime you're dealing with a marginal distribution, and I'm going to calculate a percentage, it's always a fraction here. Right? There's always a fraction. So the question is, and with all this stuff in this chapter, is what number goes in my denominator? Well, if I'm looking for, example, the percentage of women in this table, the number that goes in the denominator is the table total. Does everybody see the table total is in the bottom right-hand corner? And the table total here is 3911. Okay? So then, what I want to know, and I'm going to ask it to you like this, I want to know how many women are in this table out of the 3911. So what am I looking at? I'm looking at the row 1 total, and how many women are there? There are 2299. How many men are there? Well, I'm looking at row 2 total, and I'm looking at the 1612. We're going to need somebody with a calculator tonight, because when I punch this in the calculator, and I'm going to round to like the 10th position, and I'm going to cheat here and say the percentage of women in the table are 58.8%. What's the percentage of men got to be, even without a calculator? And how do I know that? Isn't everybody in the table either a male or a female, woman or a man? In other words, what I'm asking you is, you see this one? You see this one? Does it make sense to add? Shouldn't it? So as simple as we can do, that's the marginal distribution of sex or gender in this table. Now, I got to ask a bad question. Isn't this just like chapter 1 all over again with a categorical variable? Did I pay any attention to the degree that was earned? Did I ignore it? Did I look at just by the person's gender or their sex by themselves? And I did. Okay? All right. Let's do the other one. Every two-way table always has exactly 2 marginal distributions. This time I want the marginal distribution of, like I said, I'm just going to call it degree. So I'm looking at your column variable now. And what I want to know is what are the possible degrees that were going to be earned? Well, you could have associate. You could have bachelor's. You could have, I'm guessing the next one is master's. And then what? I'm going to put doctorate. And I'm just going to put D. I ran out of words. Right? Doctorate. Professional / doctor. So then we're going to have to form fractions. That's the thing with all this stuff again. What number goes in the denominator? See, if I start with the denominator, and everybody understands the denominator at the bottom, what number goes at the bottom, I have a shot at figuring out what goes at the top. Well, I'm looking at everybody in the table here again because I'm looking at a marginal distribution. So all of these are the same. You notice I'm using the table total in these marginal distributions as the number in the denominator. And now what I want to know is, okay, if there's 3911 here, and obviously that's 3,911,000, we chopped off the 3 zeros, all right? How many in this table have an associate's degree? And it's 1,074. How many have, I'm reading the column totals now, right? How many have a bachelor's degree? It's 1,830. How many have a master's degree? It's 823. And how many have a professional or doctorate degree? There's 184. So then we pull out the calculator and we start calculating, okay, what are these percentages? And I would appreciate if somebody would do this and round it to like the 10th position. She's ahead of me. She's going to tell me. What's the first one, associates?
27.5.
Yep.
And 21.2.
Yep.
21.
Exact?
Yeah.
Nice.
4.7.
4.7. Does anybody know what I'm looking at, or funny?
Yeah.
What was it? They didn't equal 100, right? No, so here's the question. Did we screw up? And I'm thinking, I'm going to trust you and say you didn't. What's my problem here? I'm off by, it's rounding off, right? Because I'm rounding off to the 10th position, right? And then depending on how good you are at rounding off, you might be off a 10th or 2, or in this case, it looks like I'm off by 4 tenths one way or the other.
No, one of them was wrong.
Thank you.
No, the one button didn't click on bachelor's.
Which one's wrong?
Bachelor's.
And what should it be?
46.9.
What was it?
46.9.
Oh, shit.
Or 8, sorry.
I feel better now because we're going to add to 100%, right? And then, so that's my question, is should they? Again, you might be off a tenth either way, and that would just be round off error, right? You know, the way you rounded, you're off. But we should be close to 100. And should they add to 100 exactly? If I took it all the way out as far as I wanted to take it out, I should add to 100 because everybody in here earned one of these 4 degrees, right? There's nobody missing. There's nobody counted twice. It should be 100%. So let me ask you this. That's the marginal distribution of degree of your column. Here is your marginal distribution of your row variable, the person, sex, or gender. Can I make a bar graph of these? Like I would have done back in chapter 1? Sure. Right? Okay, well look at this one. What do you notice? What sex is the majority? What do you know? You tell me the obvious thing you see. There's no, I'm not like trying to trick you. What do you see here? What's the most frequent degree earned? Oh, it goes past at 46.8, and then comes the associates, then comes master's, and way down here at the bottom, 4.7% is the doctorate professional. Why am I asking those questions? How do we always interpret a bar graph or categorical data? If you're looking at a variable by itself, you always tell me the most frequent and the least frequent, right? Remember that shit on Thursday. Somebody gives you a bar graph, and they're starting to make little statements about, you know, skew to the left or skew to the right. Do we ever describe a bar graph by telling the shape? Everybody looking at me? Everybody listening to me? So on Thursday, when you get this question, and I just had this pop into my head because I get tired of marking that shit wrong on the multiple choice test. When I give you a bar graph, and I don't care what it's about, hell, it could be a bar graph showing you this marginal distribution of degrees, right? And I look at it, and you know, you see it like it got something like that. We never describe a bar graph by telling me it's roughly symmetric, skew to the right or skew to the left, because can I rearrange the bars any way you want to? And the answer is, yes, I can. Is there a natural order there? No, there's not. Is there a natural order with a histogram? Smallest to largest. Is there a natural order for stem plot? Smallest to largest. So we can talk about shape there. We never describe a bar graph by telling me about the shape. How do you describe a bar graph? You either tell me the most frequent category or the least frequent category, which is what I just did here, right? Bachelor's degree, 46.8 is the most frequent. Doctorate degrees are least frequent. There's not really a lot to say here other than the majority are women, and obviously the minority are the men. I'm giving you the most frequent. There's only 2. Okay? Everybody understand? To me, this looks just like chapter 1, where we were looking at a single categorical variable. Why? Because I am looking at a single categorical variable. I'm ignoring the other. Right? Here I'm using rows because that's the row variable. Here I'm using columns because that's the column variable. And I can do these marginal distributions. There's always 2. You okay with that? Now, you understand, in chapters 4, 5, and 6, we're interested in the relationship. The marginal distributions tell me nothing about the relationship between the 2 variables. It just lets me talk about each variable separately. Okay? Now, there's a second type of distributions here. And there's something called conditional distributions. Now, I'm going to pop over here, and I'm on page 166. There's a box there, and they're going to tell you about a marginal distribution, they're going to tell you about a conditional distribution. I'm going to read both of them to you. Marginal distribution of one of the categorical variables in a two-way table of counts is the distribution of values of that variable among individuals described by the table. In other words, ignore the other variable. Right? We already know that. We always know there's always 2 marginal distributions, one for the row variable, one for the column variable. Now, what's of interest to us is a conditional distribution. It says a conditional distribution of variables, and I'm going to read real slow here, because it's not near as clean as, just look at the rows or the columns. is the distribution of values of the variable among only individuals who have a given value of the other variable. There's a separate conditional distribution for each value of the other variable. Here's what I'm going to tell you. I'm going to put it this way. I could be looking at the conditional distribution of sex for a given value of the degree. In other words, I either fix a column or I fix a row. Here's my thing. If there is a, can I do this? R rows and C columns. All right? So how many conditional distributions are there? There are R plus C conditional distributions. There's one where you fix every row. There's one where you fix every column. So if you have a 2 by 4 table, there will be 6 conditional distributions. Now, here's the thing. I'm going to circle those. In other words, where you start fixing the rows, they stay together in this heap. Where you start fixing the columns, they stay together in this hand. You never fix a row and fix a column and start telling me. You either look at all the ones where you fix the columns or ones where you fix the rows, and then you start looking at that kind of situation. Are we all right with that thought? So there's always 2 marginal ones. There's always R plus C conditional ones. There's R for the rows. There's C for the columns, and they stay separate from each other. Okay. We use these conditional distributions to find a relationship between two categorical variables. Okay? Now, here's what I want to do. I just want to see if I can take that table, and I just want to see if I can calculate. I'm going to do 2 of them, right? I'm going to do one where I fix a row, and I'm going to do one where I fix a column. And so, here's the way I would say this. And the language here is kind of important. I want to find the conditional distribution of degree given the person is a now. Anytime I'm asking you for conditional distribution, I'll put that little word given there because it's trying to help us. These 2 things go together. Somebody's asked me about a conditional distribution, you're giving me this word given. In other words, it's telling me what group to look at. See, what I really want is I want the conditional distribution of degree, but I only want to look at that distribution within the women. In other words, what are my possibilities here again? It's associate, it's bachelor's, it is master's, and it is the doctorate or professional. Why did I put those lines there? Well, we got to form fractions. Now, we're not using the table totals here. Does everybody see that I'm only looking at women? So then, what number am I going to use in the denominator? It's only the number of women in the table. And the number of women in the table here is, what was the number of women in the table? 2299. So I'm going to use that all the way across here. Is everybody okay with what I've got circled and how I know who's what? It's because I'm looking at the conditional distribution of degree, right? Your column variable, given that the person the person we're looking at is a woman. We're only looking at that particular row. In other words, when I look at that table, I don't even see the men. I'm only looking at the row where it's the women. How many's in there? 2299. Now, out of that row, in the body of the table, how many have an associate's degree? Well, I'm looking at the women, right? How many have an associate's degree? 673. In other words, I'm looking at cell 1. That's the one where they're women, and they have a associate's degree. Bachelor's degree in that particular row. Master's degree. Doctoral degree. Everybody understand where I pull my numbers from, right? I'm looking at the conditional distribution of degree, given that the person is a woman, and I'm only looking at the row where the women are. I'm not looking at the margins anymore, right? The 2299 is the number of women, the 673, 1050, 481, and 95 is the number in that row. What'd you get this time? Here. Yep.
Bachelor's is 45.7.
Yep.
Master's is 21.
Yep.
And doctorate is
4.1.
4.1.
Let me ask you this. If we trust her, and I add those together, what should they add? It should add to 100%, right? Because every woman fell in one of these 4 particular degrees here, so that should add to 100. If we're off by a tenth, what's up? It's round off error, correct? Now, I want to do one more of these for you in this direction because that's where I fixed a row, right? I fixed not only look at the women. I would like to do another one, and I want to do it kind of like on the same page here. I want to look at the conditional distribution of degree given this time that given the person is a man. Again, I got the same 4 categories. It's just I'm looking at a different row here. I still got associate. I've got bachelor's. I've got master's. And I've got the doctorates. So I draw a line to get you to think about, okay, well, he's getting ready to calculate percentages here while I'm actually calculating proportions and moving the decimal place. What number goes in the denominator? Who am I looking at here? I'm only looking at the men. How many men are in the table? That's my 1612. Then, in that row where you fix that row, right? That's what I fixed. That's what the given part tells me to fix. If I fix that particular row, the male, and I start looking there, well, there's 401 that have an associate. There is 780 that have a bachelor's, 342 that have a master's, and 89 that have a professional or a doctorate degree. And then we pull out the calculator, and my friend tells me
Associates is 24.9.
Yep.
Bachelor's is 48.4.
Yep.
Master's is 21.2.
Yep.
Doctorate is
5.5.
Mhm.
And again, just so we're clear, if we had rounded and everything was perfect, these should add to. If they're off by 10 either way, that's just round off there, right? So what am I looking at here? Here I'm looking at the conditional distribution of degree earned given that the person is a man. What was the one on top? I'm looking at the conditional distribution of degree given that the person is a woman. So I circled in blue because, you know, I fixed the row where you're looking at women. And I fixed the other one in blue because I was looking at the row where they were men, right? So that's my thought here. Now, to continue this one step further, you know, there's two where I fixed the rows, right? How do I know that? There's one for each row. There's one for the males, there's one for the females, right? You see any difference between these two? See that one? See that one? Let's do this. I want to come over here and they don't have my table here. They're not going to give me the data. Here's my thought. Take a look at the associates. Notice for the women it's 29.3, for the males it's 24.9. Take a look at bachelor. For the women it's 45.7, for the men it's 48.4, 21 versus 21.2, 4.1 for the doctor for the women, 5.5. Is there a relationship between a person's gender and the degree earned? There's a higher percentage of women earning an associate's degree. There's a higher percentage of men earning advanced degree. No. Remember I told you the conditional distributions are supposed to show me. I'd like to compare that one to that one. I'd like to compare that one to that one, and finally that one to that one. 21% versus 21.2, not much difference. What I see is, if I start comparing these conditional distributions for the females and the males, it looks like here there's 29.3% versus 24.9, higher percentage of women earning associates. 48.4, 45.7, looks like a higher percentage of men earning bachelors, about the same for masters, and a little bit higher, 1.4% higher for doctors. See, it looks like there is, just looking at this, there is some kind of maybe relationship between a person's gender and the degree earned. Higher percentage of the females are earning associates, a higher percentage of males are earning bachelors and doctors. What year was this? 2017, 2018, and it was projected. Yeah, that's not really the way the numbers look these days, sorry. It's a hell of a projection. That's not the way it looks. Actually, they're all flip-flop from where they should be. Turns out there's a higher percentage in the real world these days. There's a higher percentage of females earning advanced degrees than there are males. For what reason? I don't know. It's just that's the way it is. These are the numbers we're working with. Everybody understand how I calculated these? Okay? Now, I want to do one of the other ones. Notice I kept the two with the rows together, right? Because I was looking for the relationship between a person's gender and the degree earned. Yes? Let's do another one, and let's do just one of the other ones, right? So in other words, there are 4 other conditional distributions. How do I know that? Because there are 4 columns. What about if we do the conditional distribution of associates, of gender, sex, given the person will earn, and associate degree. What am I fixing now? So now I'm looking at the conditional distribution of your row variable given the value of your column. I'm just giving it to you in general terms here. And so if you're looking at the conditional distribution of gender, what are the possible outcomes? It's either a it's either women or men, male or female. What number goes in the denominator? What group am I looking at? I'm only looking at what? The first column in my table. I'm only looking at the ones that have an associate's degree. So I'm going to have 1,074. So then I look at that first column, the ones that earn an associate's degree. Out of there, how many females are there? How many males are there? Then we pull the calculator out, and my friend tells me
For women, it's 62.7. And men, 37.50.
if it doesn't add to 100%, it would then cause a round-off error because every person that earned an associate's degree was either a male or female, right? So if I'm not 100% or I'm off by 10th either way, it becomes a round-off error. Question. How many conditional distributions are there like this? How many conditional distributions are there of gender where I fix or I'm given a different degree? Right? There's 2 conditional distributions of degree given the gender. There are 4 conditional distributions of gender given the degree. You understand the language here is very, very precise. If you don't understand me with the language being very precise yet, we've got issues because why do I keep underlining that shit? Why does he circle that? Because when I see conditional distribution, I know I'm going to fix a row or a column. The question is, what row am I going to fix or what column am I going to fix? And then, why do I keep circling what you fixed? Where did I get that 1074? Those are the ones that earn an associate's degree. Back here, why did I circle women? That's the number of women I'm using in my denominator. Why did I circle men? That's the number of men that's in my... In other words, what those conditional distributions do, you don't look at everybody in the table. You look at everybody that has a certain, it's in one of the categories, either a row or a column. Now, here's my thought with all this. What I want you to be able to do with all this on Thursday is, if I give you a two-way table, can we pull out and just calculate percentages? I'm not going to ask you for an entire marginal distribution. I'm not going to ask you for an entire conditional distribution. I'm going to ask you for like a piece out of one. Right? In other words, here, I wouldn't ask you for, give me the conditional distribution of degree given that the person is a man. I would ask you for, okay, give me the percentage that have an associate's degree given that the person is a man. Oh, I'm only asking for the first chunk out of there, right? I'm asking for that 24.9. It's very hard for me to test on a multiple choice test and say, give me all 4 of those. I just want one piece of it. All right? I want to give you a little heads up, one other thing here. So, I've got percentages here so I can make bar graphs, and the whole spiel just as always. But I want to give you like a little hint, because remember, I'm looking for the relationship between, if there is one, between your 2 categorical variables. So my hint is this, and I will always refer you back to my hint. And every time I see a two-way table, I'm always going to have it in my head to call one of the variables explanatory and the other the response. That's just out of habit. So if I have, and I'm always going to make that case unless I just can't, this explanatory response distinction. In other words, I've called one of your variables the explanatory, the other one response. Remember, I think one explains or influences the other. What I want to compare here is I want to compare the conditional distributions, however many there are, of the response variable right? So think about it like this. I'm thinking, okay, I've got these conditional distributions of the response variable, whatever your response variable is, for the different values of the explanatory variable. Now, here's a little warning. Nobody says the response has to be the row, or that makes no difference. All I care is I've got two categorical variables. I'm going to think about one being the explanatory and the other being the response. And so I want to look and I want to compare the conditional distributions of the response variable for the different values of the explanatory variable. So in other words, wherever your explanatory variable is, you're either going to, if it's the row variable, you're going to fix the row. If it's the column, you're going to fix the columns and look at the conditional distribution of the other variable. All right? So, I already did it to you. With this problem here, that first table I looked at, when we were looking at a person's gender and a degree earned, I thought in the back of my head that a person's gender might help explain the degree earned. So what was I doing? I was treating a person's gender as the explanatory variable and the degree earned as the response. So what two conditional distributions did I look at? I looked at the conditional distribution of degree, response variable, given that the person is a woman. That's the value, one value, given that the person is a man. I treated it exactly like that here, right? I was thinking that a person's gender would help explain the degree they earned. I'm looking at the conditional distributions of gender given the person's, the conditional distributions of degree given the person's gender or sex. Folks, I did this right here exactly one. Except I was treating, there's no except, the response variable was the degree, the explanatory variable was the gender. Okay? Now, I would like to put all this together because to me, that's the end of the story here. There's nothing else. That's all there is in this chapter. Remember, there's always two marginal ones, and there's always a handful for the row conditional distribution, a handful for the column. I'm trying to give you a heads up here on what you want to look at when you're starting to talk about the relationship between two categorical variables. Think about explanatory and response. So I come over here to your homework problems, okay? Because that's about where I'm at this point. And I take one, let's say, like, six. Oh, I hate all these guys. Let's look at 619. I don't hate it, I just don't like the way they said it. So I'm on page 174 here. Okay? And so it says weightlifting injuries. Resistance training is a popular form of conditioning aimed at enhancing sports performance and is widely used among high school, college, and professional athletes. Although its use for younger athletes is controversial. A random sample of 411 patients between the ages of 8 and 30 admitted to U.S. emergency rooms with the injury code weightlifting was attained. These injuries are classified by accidental, if caused by dropping weight or improper equipment use. The patients were also classified into 4 age groups, 8, 13, 14 through 18, 19 through 22, 23 through 30. Here's a two-way table of the results. Now, I'm looking at this. I don't know if you can see it or not, but what I've got is my row variable here is age. We turned age into a categorical variable by making groups out of it, 8 to 13, 14 to 18, 19 to 22, and 23 to 24. Your column variable, I'm going to put type of injury. And what I mean by that is not whether you broke your foot or you broke your arm or you broke your neck. What I mean is accidental, not accidental. Okay? So I got this dumb thought here. I've got two categorical variables. Somebody's given me a two-way table. Well, so let me ask you this. So this is one that we're starting all over in. How many marginal distributions are there here? 2. There's one for the age. There's one for the type of injury, accidental or non-accidental, right? So I'm not going to mess with them again. I think those are very, very straightforward. What I want to know is there a relationship between these people's age and the type of injury, whether it's accidental or not accidental? So here's the way I'm going to attack this. I know what the book says. I'm going to attack this like this. What I want to look at, and the way I want to think about this is, I got this dumb thought that a person's age will help explain the type of injury. So I want to think about this as being explanatory, and this being your response. So what am I supposed to do? I'm supposed to look at the conditional distributions of the response for the different values of your explanatory variable, right? So I need to look at the conditional distribution of injury type, and I'm just going to, I'll put them up here as conditional distribution of injury type given So then my question is, look, I know there's going to be 4 of these, there's going to be 1 for each of the age groups, right? I want to practice with you here a little bit about, can we actually do these conditional distributions, right? So I'm going like this. What group am I looking at here? Only 8 to 13, right? So I know the type of injury is accidental, not accidental. What number goes in the denominator? It's the number in the table that are 8 to 13 years old. 8 to 13 years old. Did anybody summarize anything in the table for me here? And the answer is, unfortunately, they didn't give me any row totals and column totals and all that. But I know 295 and 102 is going to give me, what, 397? Look, what I took was, I took the 295 plus the 102. Right? And then out of the 397, how many were accidental? Well, there's 295, and there is 102. So, my friend's going to tell me my percentages this time are...
For accidental, it's 74.3. And
Like 25.7? I'm not going to underline in red and tell you that I should add to 100. If you're off by a tenth, it's because of round off there. All right? Now, how many more of these should I do? 3 more, right? There should be 4, right? There should be 4 conditional distributions of injury type given the person's age. There should be 1 for 8 to 13. There should be 1 to 14 to 18. There should be 1 19 to 22. There should be 1 23 to 30. Everybody agree with that, right? Okay. And how would I do that? What actually changes? It's still accidental and not accidental, right? What changes is the number that's in the denominator, because what age group are you looking at? And then obviously the numbers in the numerator are going to change. Yes? So I want to come here, and I want to see if we can find this file. I want to show you how Minitab will help us here a bunch. What chapter am I in? 6, and this is problem 19, right? Lifting. And I want to show you how this is actually put in here. Notice, it doesn't look quite like the two-way table that's in your book. The first column is the different age groups, the second column is the different types of injuries, and the third column is actually the count. And that's actually the numbers that's in the table, right? So 8 to 13 that are accidental is 295, 8 to 13 that's not accidental is 102, and so on and so forth. Yes? So I would like to show you a way to get out these 4 conditional distributions, because I'm going to come back here and tell you what I see is we did one of them. There are 4 conditional distribution of injury type given the age group. The reason there is 4 is because there are 4 age groups. Everybody agree with me? Remember, I was thinking an age group, the age would help explain the type of injury. So there should be 4 conditional distributions of injury type, 1 for each age group, given the age group. That's the best I can write that for you. So if I'm over here, there's a nice graph here. There's something, I got 2 options. There's something called a cluster bar graph, and there's something called a segmented bar graph. I want to show you the cluster one. If I go to graph, bar chart, right? I want, remember me and you do that all the time now about when we want to make a bar graph, no matter what style, we always do values from a table because things are summarized for us. And I want this one that says cluster here, right? Normally we just do this simple bar graph. I want cluster. And then it wants to know 2 things. Graph variable. It wants to know what column are the counts from your two-way table in. Well, it's in column 3 and it's called counts. Now, it wants 2 variables here. Okay? It wants, alright, whatever variable you put in first, I didn't test it before I came. I'm going to test it to see. Whatever variable you put in first here is going to be the given that part. So, age, injury type. Right? Remember, I wanted the conditional distributions of injury type given the age. So when I put in the age first, that's the given that part. And then I want to come to chart options, and I want to show y as a percent always. I always want to show the heights of my bars as a percentage. So I'm going to show you again. I went to chart option. I want to show y as a percent. I want to change one other thing in this box, and I want to show within categories at level 1. What I really want to give you a graph is, I want to give you a graph of these 4 conditional distributions, if I've got my order right of my 2 guys there. All right? So I always do that change there. Anytime I'm looking at conditional distributions and I got 2 categorical variables and I'm looking at relationship, I always go in there and show y as a percent, and then within categories at level 1. If I didn't screw anything up, I should be showing you 4 bar graphs. 1 for each age group, right? So, you see this first one here, 8 to 13? I just made you a bar graph of that. Now, you know we can hover. 74.3%. 25.7, she was correct. Right? So I am showing you the 4 conditional distributions of entry type given the person's age. Notice at the bottom, the ages, right? That's the given that part. The next row up is your conditional distribution of that variable. Everybody understand how I did that? Now, if I take that 8 to 13 and I stack the bars together, what should the height of those bars be? They should be 100%, right? Because everybody fell in one of the 2 types of injury. Are we okay so far? See, because we haven't got to the punchline. The problem wants me to compare. I chose to compare the 4 conditional distributions of injury type given the person's age group. I got lazy and didn't calculate all 4 of the conditional distributions. I calculated 1. Right here is the graph of that 1. And the way I showed you how to do that, many had calculated the other 3 for us. How do I know that? Because if I hover, that's going to be whatever the percentage is. Maybe 41.7%, 58.3%. In other words, those numbers I'm showing you, that right there is the conditional distribution of injury type, given the person is 14 to 18. This one right here is what? This is 30.31. This one should be 69 then. That is a conditional distribution of injury type, given that the person is 19 to 22. Cheat again. 26.5, 73.5. That's the conditional distribution of injury type given the person is 23 to 30, right? So what this cluster bar graph is, that's what it is, right? I've got 4 bar graphs, one of each conditional distribution on the same picture here. It's allowing me to compare my 4 conditional distributions without me having to do all the calculations. What I want to know is there a relationship between a person's age and the type of injury? What I am asking you is, do you see the 4 bar graphs? There's 4 of them separate. Do you see the 4 conditional distributions? The answer is yes. Do they all look the same or do they look different? Does this one does that one look different than the other 3? And the answer is yes. In the 8 to 13, the highest percentage, the majority have accidental injuries. In the other 3, what types of injuries are the majority? Non-accidental. What was an accidental injury? You dropped the weight on your foot. What's a non-accidental injury? You were so stupid you tried to pick up too much weight and you hurt yourself. So is there a relationship between a person's age and the type of injury from weightlifting? And the answer is yes. The younger children are more likely to be hurt by an accident. The older you get, okay, look at these. I don't know how else to do this other than start circling stuff. Look at these 3. The older you get, the more likely you are to hurt yourself by doing something, I don't want to use that word, stupid. Right? Because look, we're going 14 to 18, 19 to 22, 23 to 30. Hell, when you get up to 23 to 30, you're more likely to do something by hurting yourself stupid than dropping the weight on your foot. When you're younger, you're more likely to drop the weight on your foot. Is there a relationship? Yeah. As you get older, I guess we get dumber. Sorry. I'm just translating. Do you understand what I'm asking you? So, I'm asking you, when somebody wants to know, look, this is the nice way to do this. This is what's this called? A cluster bar graph. That's a graph, and what is it doing? I can spin it any way you want, but what it's showing you is this. It's showing you the 4 conditional distributions of injury type given the age. And then somebody's going to come back and ask you, well, looking at this, is there a relationship? Well, yeah. What they're asking you when they ask you for a relationship is do these 3, 4 conditional distributions, these 4 bar graphs, do they look the same or do they look different? Now, you understand they're never going to look perfectly the same. You understand that? So what we really want to know is they look a lot different. That's the reason I chose this problem. Because the first one is completely different than the other 3. Hell, the height of the bars are flip-flop. So is there a relationship? Yeah. If you're young, you're more likely to hurt yourself on accident. The older you get, the more likely you are to hurt yourself by doing something you shouldn't. Yes, there is a relationship here. Now, I've got to show you the other graph. This is the one. This is my go-to guy here when somebody wants me to compare 2 categorical variables out of a 2-way table. But just to show you, there is another option here: graph, bar chart, values from a table. There's something called stack, right? So instead of the bars being for each categorical variable, for each conditional distribution, they'll make 1. I want stack. Same idea. Where's the count? What did I put in first? It's the given that part. Age, injury type, chart options, show Y as a percent. Either way, I always do that, right? I went to chart options, show Y as a percent. The bars heights are going to be in percentages within a category at level 1. Maybe you see it better here. So I'm showing you the 4 conditional distributions of injury type given the age group. This time, the age groups are along here. The injury type is a different color. Can everybody pick out that in the 18 to 13, around 70-some% are accidental, and as you get older, what happens? There's a higher and higher percentage of not accidental. The younger you are, the more likely you are to hurt yourself by accident. The older you are, you're more likely to hurt yourself by doing something you shouldn't be doing. Is that the same picture as the other one? What they do, they just took the bars and stacked them on top of each other, right? You might like that picture better. I always go to the other one because I'm so used to looking at bar graphs, see if things look different or the same. You understand, do these 4 bars look different? They're completely different, right? The first one's completely flip-flop from the other 3. The other 3, you're starting to see more and more red as we go out over and over and over. All right, so you're ready. I mean, that's all I was going to do here anyway. So we're going to have our test on Thursday. I want to say one more thing about the test. So I told you to bring your calculator and your formulas and tables, right? What I'm going to give you is I'm going to give you a test and an answer sheet because it makes my life a little easier to grade if you've got like 1 through 20 and 21 and you put your little letters there. I'll remind you that on Thursday, but that just makes it a little bit easier for me to grade things instead of going through all the papers. Be careful going to the house, and we will see you on Thursday ready for the test.
Hey, Mike.
Yeah, bud.
Very briefly, I found 2 homework 3s that have been in my possession the entire time, and they were turned in. I'm going to turn them in with the test, just so you know that, okay?
So they was turned in on time?
They turned them in on time. Been with me the whole time. They just got caught in a folder that I didn't know that they were in.
Let me ask you this. What's their names?
What's your name?
Darren?
Darren and Joanna.
Yeah. That makes sense because I was wondering where they were. I figured the hell they just emailed them to me. Yeah. Send it to me and I'll grade it and then I'll send it back to you with the test and we'll all be good. That makes more sense to me.
It was all my fault.
No, that's cool because, I mean, I was expecting, because they've been doing fine, I was expecting them to send it. Yeah, that's cool, man. Just send it to me in the test and I'll grade it. And then you can give that back to them next Tuesday too, bud.
I just want to